On this practice, we are going to test the 1045 steel. We cut four different pieces and we make them heat treatment. The first one, we leave it like it was. The second and the third and the fourth, we put them into the oven at 900 Celsius degrees for 12 hours. After that, we took out just one piece and the other two, we put them into the oven at 800 Celsius degrees for 15 minutes. And finally, we put only just one piece in the oven at 200 Celsius degrees for 15 minutes. After that, we put them into backlights in order to analyze them after doing the Vickers test. There are some concepts we need to understand before we initiate this practice. The first one is carburizing. This is a heat treatment that changes the mechanical properties, making the metal resistant to wear and maintaining the toughness and the strength. Then, the carbon equivalent. This is an empirical value in weight percent that relates the combined effects of different alloying elements used in the making of carbon steels to an equivalent amount of carbon. This indicates the maximum concentration of carbon that reaches the surface of carburized. This potential is determined by analyzing shavings of the treated sample. It's the carbon that covers the surface of the piece, giving it more thickness. This layer gives a hard cover to the metal, giving the surface more strength and hardness, but maintaining in the inside the same ductility. It's the atoms and ion movements that change the mechanical properties of the metals. There are three different types, that is interdiffusion, interstitial, and vacancy diffusion. Tempering involves heating the metal to a precise temperature below the critical point and is often done in the air, vacuum, or inert atmospheres. It is soaking of a metal at a high temperature above the recrystallization temperature and then cooling it fastly for getting some mechanical properties different than the original ones.
For the applications of the cementite in the metal industry, we found that it's important for car parts, also for parts that need to have a hard surface and a rigid center nucleus. Also, it's very important for gears, cams, and a very strong surface. Why is important this cementite in this type of industry? Because this cementite give the properties that a very rigid nucleus and a very hard surface. So that's the application for the industries in metals for cementite. Different type of steels for cementite. We find the steel for carburization, that is the loaded density application of, for example, the steel carbon cementation is for loaded and reduced thickness part, and also the steel for chromium and nickel is for the parts that need to have a high surface and very strong surface. So that's the characteristic of those two metals. Also, for the steel with chromium and molybdenum, it has the characteristic of transmit high stress, and also a very particular and a very quality of this carburization is the chromium, nickel, and molybdenum that has a very good tenacity and a great surface hardness, and it's used, for example, for motors.
Now I'm going to talk about the types of cementation. The first one is cementation in a box, that it involves to put the pieces in a stainless steel box and put it with an cementitious agent, and then put it in an oven to take the time for carburization. This method is so slow and it's not so used in industry. Now the last type of cementation is cementation in gas. This includes to put the pieces in an atmosphere composed of hydrocarbons. This is a quick and exact method, and you can put a lot of pieces at the same time. Describe a phase as an homogeneous part of the system that has specific characteristics, physical and chemical characteristics that define a phase. And by the other way, a microconstituent we can define as an identifiable part of the microstructure that can have many phases.
Now I'm going to explain some common equipment used in the industry for heat treatments. But we have typically electrical furnaces and gas furnaces. But in this case, I'm going to explain the the gas ones. And one kind of gas furnace is the direct fire, that are like when some burns is like warm directly the furnace, like a cooking pot, and that's the first one. The other process is the indirect fired process, that when you have like radiant tubes that radiate a lot of heat to your piece, and it could be also a muffle or a torch. And that's the second process. You also it's common to know another process, that is the molten salt process, but it's when you have a lot of salt and then it is warm, like up to 8 Celsius degrees, and you immerse your pieces here there, and after some period of time you take out the piece and quench in water. Now I'm going to explain how we calculate the depth of the carbon layer on our pieces. So, well, we're going to use this formula, and we have this data. This is the percentage of the atmosphere at the surface of our piece, of our material. C sub S, we have 1% of carbon. The carbon that we need is C sub X, that is 0.45%, and our initial carbon percentage is 0.1%. Now we use substitute here, and to earn this value, the left part of the formula, we got 0.6, that is our receipt. And now we want to complete the other part of the formula. So we need the diffusion, and then we need the diffusion formula, that is this one, and we have these parameters. So we just compute, solve for diffusion, and we replace the results here in the original formula, or the first one that we are using, and we clear for X. So our final result is that our layer of carbon depth is 0.1070 centimeters.
Metallography practice, we can analyze each of the three pieces that we have. In the first one, that only been 12 hours in 900 degrees, we count 8 grains, and with that we can obtain 9 STM number of grains. Then with the second one, that it was another 15 minutes in 800 degrees, we count 14 grains. We obtain 10 as the HTM number of grains. And for the last piece, that is another 15 more minutes, about 200 degrees, we count 7 grains, and with that we obtain 8 number of grains of the STM. With that, we can say that if we do a carbonization, the number of grains is going to increase and the size of the grains is going to decrease.
A very particular steel is the chromium and molybdenum. It has, and I want to mention it, is because have the characteristic of transmit a very high stress. Also has the characteristic to support a good tension, and in the surface is very hard. That material is used also for gears, cams, and also for cars parts. So that's why it's a very particular and good material to use in the industry. For the changing the properties about the samples, when we got it to carburize it, first of all we took the sample and put it in the carburizing process for 12 hours at 900 degrees. For after that, we got all the material was completely austenite, and then we took out a sample and put it in water to undercool it, and then we again put the material and got for 800 degrees to convert again on 10% austenite, and then we got out again and undercool it in water again. After that, we took all the material and put it for 200 degrees only. Then the process will be completely different because we got unstable perlite. So after that, we can conclude that with that heat treatment of 200 degrees, we got more hardness of the material and got better mechanical properties.
For the first and second stage that are in 900 and 800 degrees, we can see that the Rockwell sharpness are lower than 14. And for the third stage, that is at 200 degrees, we can see that it's in the 57 Rockwell sharpness.
After doing the Vickers test, we obtained the hardness for the 3 different samples we had. For the first one, that was only 12 hours at 900 Celsius degrees, we obtained this graph, where we can see that the hardness augmented from the exterior to the interior, but just a little bit. So we moved to the second piece that was 12 hours at 900 Celsius degrees and 15 minutes at 800 degrees. There, the hardness exterior improved and the interior also, but in less measurement. And the final one that was 15 minutes at 200 degrees, we can see that the hardness augmented a lot because of the heat treatment, and also we can see that there is a difference between the exterior and the interior of the piece. This is the proof that heat treatments and all of these process can help to make pieces for geared pieces and all of the.
Opinion this practice is very important one because it will help us to the future projects because we got the knowledge about how the how a metal develop with cement type process, uh, how what properties give to the metal about how much hardness will improve to the metal and all those things. I think that this practice was very active and also helped me to enhance the knowledge that we got in the classroom.
In this practice, I found very interesting the process of carburization. Personally, I has a big interest in gearboxes, and this process is very important in this kind of components because our gears and the process of heat treatment, it's very important to enhance the structural parameters of these kind of components.
That was very amazing. I think carburization and all the heat treatments that are around the industry are like the soul for mechanical engineers because in this way you can change the properties as you want with the metal you have, and you can transform it in order to have the properties you want for your application.
I learned how heat treatments are made of and how with these treatments we can change the mechanical properties. And also I understand how the carburization process is made to the materials in order to improve the mechanical